Hello and welcome to another episode of Maths with Mrs. Banks, where we make maths fun and easy to learn. And in this video, we're going to look at Theorem 4 of circle geometry, and this is for mathematics grade 11. And the theorem goes angle at center equals twice angle at circumference. And here is a summary of what the video is going to cover. We're going to look at step number 1, know your theorem. What is the theorem about? And number 2, we're going to look at the goal. What are we required to prove? Number 3, we're going to look at the strategy. Step number 3, the strategy. How do we go about achieving the goal? Number 4, we're going to look at how to apply Theorem 4 using examples from past exam papers. We have a lot to cover, so let's start. The theorem goes angle at center of a circle is twice the size of the angle at the circumference. Here is step number 1. We need to figure out what the goal is. Step number 1. Let's look at step number 1. Fix that. Sorry about that. Step number 1. No. Step number 1. Know your theorem. What does the theorem say? Step number 1. Know your theorem. Let's know the theorem. Let's define some words so that you understand exactly what they are about. Now the statement goes, if an arc subtends an angle at the center of a circle and at the circumference, then the angle at the center is twice the size of the angle at the circumference. Now to subtend, you can call it like something like to suspend something. You know when you get a hanger and then you hang something or suspend a piece of clothing. We're going to think of subtend like that. I know it doesn't necessarily exactly mean that, but I just want to give you a visual that will make it easier for you to remember how to. So to subtend is to hang or suspend an angle, and I'm going to show you how the suspension happens. And the circumference of a circle is the edge of a circle. So the angle subtended or hanged at the center of the circle by an arc is twice the angle subtended or hanged by the same arc at the circumference. And the reason we use for this one is angle at center is equals to angle at circumference. Angle at center equals to twice angle at circumference. There is the reason. Let's start. So we're down on step number 1. You know what the words mean, or at least have a visual and understanding of what they're about, and then you know where the circumference of the circle is. All right, step number 2. Now that we know what the theorem is, now let's figure out what the goal is. What is the goal? What is the goal? What are we required to prove? Here is the goal. In fact, this is where we should put number 2. Step number 2. The goal. What is the goal? What are we required to prove? We are required to prove simply that angle AOB is equals to 2 times angle APB. That's what we are required to prove, that this angle over here is twice the angle at the circumference of the circle. Here is the circumference. So both these angles are subtended by arc AB. There is the arc. It subtends. Notice that the suspension AOB is subtended at the center of the circle. There is the center of the circle. So it goes right to the center. It's hanging at the center of the circle. And angle APB is hanging at the circumference, the edge of the circle. And that's so we're required to prove that this angle here at the center is equals to 2 times the angle at the circumference. Now now that we know what the goal is, what is the strategy? Step number 3, the strategy. So let's fix this. Step number 3 will be the strategy. All right. Step number 3, the strategy. What is the strategy? How are we going to go about this? The strategy for this one is actually very easy. If you join PO and produce it all the way to Q, you will end up with 2 triangles And those two triangles, you can manipulate them to show you something. I'm going to show you exactly what I mean by that. You end up with two triangles, the triangle APO and triangle BPO. Now, these triangles will be isosceles triangles, and then we will use the exterior angle of a triangle to show that this is 2 times that. So step number 1 is to use triangles particularly the exterior angle of the triangle. Okay. Number 2, cut them into 2. Cut them into 2 and work through them one by one. Work through them one at a time. One by one. That's the strategy. Let's go. So here is the strategy. What is the proof? Okay, so we made the construction, join PO and produce it all the way to Q. Join PO, this is the construction. So the construction is join PO and produce it all the way to Q. Join PO. I'm sorry about that. Join PO. Join PO and produce it to Q. And produce it to Q. Get that all the way to Q and divide this angle as into 2, angle O1 and angle 2. Now you have triangle APO and triangle BPO. Now here is the proof. In triangle APO, there is triangle APO, triangle APO. In triangle APO, angle O1 is equals to this angle and that angle. Now let's call this angle X and this angle A. Let's call this angle Y and that angle B. Angle O1 equals to A plus X. Angle O1 equals to A plus X. And that is simply the exterior angle of a triangle. Exterior angle of triangle is equals to the sum of the angles interior opposite and the interior opposite. Okay, but notice that PO is equals to AO, equal radii, but PO equals to AO, and the reason is equal radii. Now that we've got these equal radii, that means therefore angle A is equals to angle X. Therefore angle A is equals to angle X. Therefore angle A equals to angle X. And the reason is base angles isosceles triangle. Base angles of isosceles triangle, or you can just say PO equals to AO. Base angles isos triangle. Therefore, angle O1 will be X plus X. Therefore, angle O1 will be equals to X plus X, which is 2X. Alright, so we've proven the half of it. So O1 is equals to 2 times this part, X. Now let's do the same for triangle BPO. triangle BPO. Let's do the same for triangle BPO. All right, angle O2 in triangle BPO. In triangle BPO, angle O2 equals to y plus b. Angle O2 equals to y plus b. And the reason is exterior angle of triangle. Exterior angle triangle. But same story. But PO equals to OB, equal radii. But PO equals to OB. But PO equals to OB, and the reason is equal radii. That means equal radii. Therefore, that means angle Y equals to angle B. Angle Y equals to angle B, base angles of this isosceles triangle PBO. Therefore, angle Y equals to angle B, or angle B equals to angle Y, meaning that therefore angle O2 will be equals to Y plus Y, which is equals to 2Y. So far, so good. Now, let's complete the work. Now let's add angle O1 and angle O2. Now angle O1 and angle O2 will be equals to O1 is 2x and O2 is 2y. So that will be 2x plus 2y. And all we do now is we take out a common factor. Therefore, angle O1 plus angle O2 equals to 2 in bracket x plus y. But notice that angle O1 and angle O2 is simply equals to angle AOB. Therefore, angle AOB is equals to 2 times. And also notice that angle x plus y, angle y is simply equals to angle APB, angle APB. And that's how you prove it. They're proven. And that's how you prove that. Easy if you ask me. Next, let's look at some questions from past exam papers. This one comes from the Gauteng paper. I don't remember what year. I didn't write that down. I'm sorry about that. Let's look at question 9. 9.1 says, in the diagram below, O is the center of the circle passing through P, Q, and R. Chords PQ, they're PQ. Chords PQ and PR, they are the chords, are drawn with OQ and OR joined. Use the diagram provided in as to prove the theorem that states that the angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at the center of the circle. In other words, angle ROQ is equals to 2 times angle RPQ, or simply 2 times angle P. That's the theorem we just proven now. So let's go. We make a construction, step number 1. There is the construction. All right. Let's divide the page into 2 sections so that we can work. All right. Let's change the color. I just like the color better. All right. Now let's start. All right. So proof. Remember? Okay. Let's make a construction. Construction. We joined PO and produce it to T. Join PO and produce it to T. Join PO and produce to T. Label this 1 and label that 2. Label this x, label this y. Alright, now angle O1 equals to, okay, label this B, label this A. Angle O1 equals to y plus b or b plus y. Angle O1 equals to b plus y, and the reason is exterior angle of a triangle. There. But angle OR is, side OR is equals to OP, equal radii. Side OR equals to side OP, but OR equals to OT. Is it OT? No, it's OP. But OR equals to OP, equal radii, equal radii. Therefore, angle B equals to angle Y, base angles of isosceles triangle. Therefore, B equals to Y, base angles of isosceles triangle. You can simply say OR equals to OP. Base angles, isosceles triangle. Now, therefore, angle O1 is equals to y plus y. Therefore, angle OY equals to y plus y, which is equals to 2y. We're done with O1. Let's do the same thing for O2. Angle O2 equals to x plus a plus x, and the reason is exterior angle of triangle, exterior angle triangle. But OP is equals to OQ, equal radii. But OP equals to OQ. Reason, equal radii. Therefore, angle A equals to angle X, base angles of isosceles triangle. Therefore, A equals to X. Therefore, A equals to X, and the reason is base angles, isosceles triangle, or you can simply say OP equals to OQ. Now, therefore, angle O2 will be equals to x plus x, which is equals to 2x. Now let's add the two angles O1 and O2, which is angle ROQ. Now angle O1 plus angle O2 equals to, O1 is equals to 2y, O2 equals to 2x. So that will be 2y plus 2x. So what we do now is take out a common factor. Therefore, angle O1 plus angle O2 equals to 2 in bracket y plus x. But notice that angle O1 plus angle O2 is equals to simply angle ROQ. Therefore, angle ROQ is equals to 2 times. Also notice that angle y plus x is simply angle RPQ. So that will be 2 times angle RPQ. And that is how you prove theorem. Easy, very easy theorem to prove. Next, let's look at question 9.2. In the diagram below, DF is the diameter of the circle with center O. The DF is the diameter with the circle center O. Chord EG, there is EG. Chord EG intersects DF at H, such that DF, there is DF is perpendicular to EG. There is then 90 degrees. And you know that with 90 degrees, it means that all the angles there are 90 degrees, all of them. Chords EF and GF, there they are drawn. Angle EGF is equal to 55 degrees. There is that 55 degrees. Determine, giving reasons, the size of angle D. There is angle D. The size of angle D. Notice that angle D is subtended by the same chord with angle D is subtended by the same chord. There it is subtended by this chord EF, and the EF also subtends angle G. So therefore angle D is equals to angle G, which is equals to 55 degrees. Is that angle G? Yes. And the reason is angles in same segment. Angles in same segment. Angles in same segment. Angle O2. This is subtended at the center. This angle O2 is also subtended at the center by the same chord EF. And we know that this is 55 degrees. So therefore, this is equals to twice angle G, meaning that this is equals to 2 times 55 degrees, which is equals to 110 degrees. And the reason is angle at center is twice angle at circumference. Angle at center equals twice angle at circumference. And that's the reason. Angle at center equals to twice angle at circumference. So there it is. E2. Angle E2 is right in the middle. Now notice that angle D is 55 degrees. Okay, let's just note that. So angle E2 is very easy to find. Now that we know that this is 110 degrees, these two, because these are equal radii, these two will be half of the remainder. So let's take our time to find angle E2. So this is number C. Okay, let's find angle E2. We're looking for angle E2. Alright, to find angle E2, we need to use all the angles in that vicinity. So let's find angle E1 first. Angle E1, angle E1, angle E2 will be equals to, okay, so first of all, angle E. First of all, angle E is equals to 90 degrees, and the reason is it's an angle in a semicircle. There is the diameter DOF, and this is the angle subtended by 180 degrees, so that makes it 90 degrees, and the reason is angle in semicircle. Angle in semicircle. Now that this is 90 degrees, let's find the rest of the angles. Angle E1 is equal to 180. Angle E1 equals to 180 degrees minus the sum of the other two. That is sum of angles in this triangle DEH. So that will be 180 minus 90 minus 55. 180 minus 90 degrees plus 55 degrees, which is equals to, take out a calculator, 180 minus 90 plus 55, 180 minus in bracket 90 plus 55, and that gives us 35 degrees. So that is 35 degrees, and the reason is sum of angles in a triangle. That's what that is. So this is 35 degrees. Let's pencil it in. Always pencil in whatever answers you get. And then this one, angle E3, is a base angle of this isosceles triangle EOF. We already have got 110 degrees, so the rest will be, so angle E3 will be equals to half of whatever we have there. It will be 180 minus 110 over 2. 180 minus 110 all over 2, which is equals to 180 minus 110, 180, common fraction button, 180 minus 110 all over 2, and that will give us 35. So that gives us 35 degrees, and the reason is base angles isosceles triangle. Sum of angles in a triangle, base angles. Sum of angles in triangle, or you can say base angle of isosceles triangle as well. Base angles isosceles triangle. It's up to you what you want to write. So that is 35 degrees. Let's pencil it in. And now that leaves us with the remainder, which will definitely be 190 degrees minus this 2. So therefore, angle E2 will be equals to 90 degrees minus the sum of these 2, which is equals to 90 minus 70, 90 minus 35 plus 35, and that gives us 20 degrees. And the reason is sum of angles in a triangle. Sum of angles in triangle. So that is 20 degrees, and that is how we find that. So therefore E2 is equals to 20 degrees. You can just say sum of angles in a triangle. Next, let's look at angle E3. Oh, angle E3, we just found that. Angle E3. Alright, angle E3, we just found angle E3. Angle E3 equals to 35 degrees. You can just say base angles isosceles triangle. Alright, next question. Determine the length of OH if the diameter of the circle is 10 units and G is equals to 9,4 units. The diameter there is 10 units, so meaning that this radius will be, the radius will be 5 units. Okay. Radius, and we're looking for HO. The radius, which is DO, will be equals to EO, equal radii. The radius will be equals to half diameter, half times diameter, which is equals to half times 10, which is equals to 5 units. That's the radius. But the radius is also equal to the same amount everywhere. So this is 5 and that is 5 units. This is also 5 units OD. So it's OD, OE, and OF are all 5 units. Okay, let's point that out. OD equals to OD equals to OE equals to OF equals to 5 units. OD, OE, OF all equal to 5 units. reason equal radii. They are all equal radii. So now we've got this OE in a right angle triangle equals to that, and then we are told that GE is equal to 9,4 units. But notice that GE is a chord that is perpendicular to the line through the center of the circle OH. So meaning that therefore OH bisects GE, meaning that EH is equals to HG, and each one of them is half GE. HE equals to half GE equals to half 9,4, which is, okay, let's go 9,4 divided by 2. That gives us 4,7. 4,7 units. And the reason why it is half is OH, okay, line from center bisects chord. Line perpendicular to chord. Line perpendicular to chord. Line from center perpendicular to chord bisects chord. Alright, therefore now we've got 4,7 units. So this is 5 units, and then we've got 4,7 units. Oh, sorry, this is, we're looking for HO. This is a right angle triangle, so it will be easy to find HO. Alright, so OE squared equals to the other one squared plus the other one squared. I'm going to find them, and the reason is Pythagoras. I just want to get this sorted. So OE squared is equals to HE squared plus HO squared. HE squared plus HO squared. HE squared plus HO squared. Now OE is 5 units. HE is 4,7 units. So let's substitute. Always substitute because you get marks for that. HE is 4,7 units, and the one that we're looking for is HO. Now what we do is we take everything to the left hand side. 5 squared minus 4,7 all squared equals to HO squared. Now let's sort this one out. Therefore, okay, let's draw a line. We'll just ignore this. I don't want to go to the next page. I want to go everything done in one page. Therefore, the square root of 5 squared minus 4,7 all squared, and that is equal to 1,705. Therefore 1,7 units is equal to HO, and that is the answer to HO or LH. It's up to you. 1,7 units. And with this, we've come to the end of this video. Thank you so much for watching. I'll see you in the next one.